In this video, we're going to continue our discussion of Linux File I/O and cover the remaining portions that we haven't covered in Linux System Programming Chapter 2. So some of the learning objectives, we're going to talk about how to access files positionally. We're going to introduce the idea and concept of sparse files, which we've actually mentioned briefly in previous weeks. And then we're going to introduce the idea of multiplexed I/O. So reading positionally, you might have had some experience with this already with the F versions of Open Read and Write. So if you want to, rather than just read from the beginning to the end of the file in sequence, if you need to change that up and need to read from different parts of the file or need to write to certain areas of the file, you can use lseek to do this. And there are a couple different options in terms of how to locate within the file with lseek. And these are the same options that are offered for the buffered I/O as well. So seek set means you're just going to use the specific offset that the byte offset that you mentioned inside the file. You're going to just use that relative to the beginning of the file. That's going to be an absolute position that you want to seek to. The seek current says wherever I'm at, I'm going to increment or decrement based on the offset I specify into the file. And then seek end means I'm going to seek relative to the end of the file. So I'm going to, if I say -1, I'll be 1 byte before the end of the file. The book also mentions some alternatives for positional read or write based on an alternative to the lseek command or the lseek function I mentioned earlier in pread and pewrite. So one benefit of these is if you're using the lseek command, you're going to be modifying the position for any of the threads that are running in your process. So you're basically setting the position globally for your process on that file descriptor. But if you use the pread or pewrite versions, you're not going to specify the origin. You're not going to specify the location for all threads. You're going to be specifying the location based on this one particular read or write command and where it's going to go into the buffer. So benefit would be if you're using a multi-threaded application, it's not going to manipulate file position for other threads. And in order to simplify this a bit, the origin argument is removed and you're always going to use the equivalent of seek set, in other words, just an absolute position into the file for locating. So talking a little bit more about sparse files, if you use lseek and let's say you search into a gigabyte offset based on seek end, so in other words, I'm going to locate from the end of the file 1 gigabyte out on my current file descriptor, and then maybe I just write one value, unsigned integer value, let's say, out to that location. This would extend the file 1 gig past the end of the current file location. So what if there's less than 1 gigabyte of disk space available? Would you expect this command to fail? And maybe you would, just thinking about what it's doing, but in reality, the Linux file system is smart enough to know that you didn't actually write a gigabyte of data. You just extended the file out that long and wrote 1 byte past the end. So the Linux file system is actually smart enough to not use disk space in this case. Instead, it'll create a hole to represent the space in the file that hasn't been written. And if you read the file, it'll look like it's a contiguous block of values, but in reality, when you're reading the hole that hasn't been written, it'll just be returning zeros. And this is what's referred to in Linux as a sparse file. So if you want to see an example of this, again, you can follow the link from the lecture notes. But here's a case where you can create a sparse file using the sparsefile.c application by doing an lseek relative to seek end based on the parameter specified, and then writing a single byte at that location. So how can we see what's happened here in terms of disk space usage? What you'll notice is that sparse file that we create, if you do ls-lh, so this is going to say list and give me a human readable representation of the file size. What you'll notice is that the ls command says that the file is 954 megabytes in size. So roughly 1 gigabyte offset that we specified here with the sparse file parameter. But if I use du, which is the disk usage command, and I list the human readable size for every file in the directory, I'll see that the sparse file is actually only using 4K of disk space. So this is a way that you can tell that the file is actually a sparse file. Okay, so if let's say your application needs to handle input from more than one file descriptor at once. And if you're using something like a FIFO or a pipe as one of those file descriptors, and you would normally have a behavior where you're blocking, waiting for some input from the file descriptor, you have a couple different ways to handle this. So two of the ways are the ones that we've already talked about. One would be you just create a thread for every descriptor and you just do the typical blocking reads. So if you have some other work to do, you just spin up another thread, but you have a thread that's dedicated to doing blocking reads on the FIFO or pipe. And it's okay that it's blocking and waiting for data. A second option would be that you use non-blocking I/O or O non-block that we talked about in the previous video, and then you pull with your application. So you keep trying to read, and if there's data, you do something with it. If there's not, you do something else that the thread needs to do. But the book also mentions multiplexed I/O as a better solution than polling, because what it allows you to do is sleep from one thread until a set of file descriptors is available. So in other words, rather than needing to have a dedicated thread for every file descriptor, maybe you're in a situation where you want to handle any of a bunch of different file descriptors. You want to handle I/O on any of those file descriptors whenever they occur, but you'd rather not have to spin up a separate thread to monitor each one of them independently, and you'd rather not waste the cycles of continuously polling and doing nothing other than polling every one of the file descriptors forever. So there are three different options to do this: select, p-select, and poll. The book mentions that poll is actually the preferred mechanism of these based on the flexibility that it offers. But all of them essentially do the same thing, which is take a list of file descriptors that you want to watch and sleep until something happens on one of those file descriptors, at which point you'll get a notification from your application that you need to handle it.